Hello everyone, welcome back to the latest lecture session. A quick recap of what we discussed in the previous session. In the previous session, we were looking at how much water to supply and until what period are we going to supply the water. And obviously in this session, we are going to take it to its natural conclusion. We are going to look at what is the kind of water that we are going to supply. For example, in the context of wastewater, we were discussing BOD, COD and relevant parameters when we were trying to understand the strength or the quality of wastewater. But obviously, we won't be using the same parameters when we are talking about water quality, right? So, let's look at these aspects or water quality relevant standards. Before that, just an overview. What am I typically concerned with? I am concerned with seeing that there is little to no disease transmission or pathogen transmission. So, I am almost always concerned about pathogens, right? I am concerned about pathogens. So, this is the most important aspect to keep in mind. There might be, if I am using groundwater, there might be deposits or contamination of groundwater due to various sources, right? So, maybe then I need to look at a particular treatment mechanism for that particular kind of toxic compound. But in this course, we are going to look at the general aspects. So, after the pathogens, we will look at toxins or such, but again typically relatively rare cases. So, we will not go into that right now. Another aspect obviously that we typically almost always consider is total dissolved solids and total suspended solids, right. So, these are indirect indicators. So, that is the relevant issue, as you know, total dissolved and total suspended solids. The sum will be equal to the total solids obviously. Total suspended solids again will give me an idea about pathogens and quality of water, but it is not a direct correlation, but it will give me a pretty good idea. And dissolved solids will give me an idea about how much or how many ions or such there are in that particular water. Too high, difficult, too low, not fit for consumption. Let us move on and look at the relevant aspects. So, typically when we talk about water impurities, we look at physical parameters to be able to estimate this water or water impurities, and then chemical and biochemical and then microbiological parameters. In the context of wastewater, we looked at these, but in the context of water or drinking water, we will not look at this, right? We will not look at this. What do we typically look at? We look at the physical, chemical and microbiological parameters. So, total suspended solids, we looked at that. How do we measure that? That is using the turbidity meter, and the units are NTU. TDS, total dissolved solids, yes again, and we can measure that by conductivity or by direct measurement. We look at the color of the water, temperature too. For taste and odor, there are some tests, but in India typically if it is not objectionable, that is good enough for us. When we talk about chemicals, we look at the usual cations and anions. Here anions, I guess, negatively charged, that will at higher concentrations, lead us to have, let us say, some diarrheal issues or digestive issues or such, or maybe pain in the joints and such. So, we have those some cations, let us say Fe2 plus, Mn2 plus, right, cations positively charged. This is 2 plus, if it is not clear, 2 plus, right. And then hardness, because if the water is too hard, meaning I have too high a concentration of calcium or magnesium, right, the bivalent cations, that will, not let my surfactant or soap form the relevant leather, right, and I will have issues whenever I am trying to clean my utensils or clean myself or the clothes, right, and also it can lead to scaling of the relevant pipes or utensils and such. So, that is an issue. And again heavy metals, which can lead to toxicity, again arsenic, right, and fluorosis too due to fluoride, let us say, but we are not going into detail right now though. Microbiological, so we have pathogens and typically viral particles, but viruses in general come under the category of pathogens, let us say. So, typically we are concerned with microbiological parameters too. So, let us look at where I can get this data. So, there are different sources. One is this particular link that you can copy paste and look at, right. So, relevant tables in standards, I am going to look at the standard, but let us look at the general classifications or characterization. So, first one is organoleptic and physical parameters. So, the general parameters which we discuss, which we measure when we talk about water or water quality. Then the parameters which when excessive will have undesirable effects, right. But again, copper will also have toxicity, so that will come there, and also in toxic substances, right. Typically, I am concerned about hardness, alkalinity, ammonia, iron, and so on and so forth. Table 3 about toxic substances, heavy metals, typically cadmium, lead, trihalomethanes, which are the disinfection byproducts we already discussed, and so on and so forth. And radioactive substances, but rarely do we measure this in drinking water because, okay, for example, I think there is a student group here in IIT Roorkee, Unnat Bharat Abhiyan. They were trying to look at the water quality of a particular village, or the water from the quality of the groundwater that's being consumed by villagers nearby. So they say, Banu, get the test done. Okay, I say for what parameters? So then obviously they are not sure, because as you see, when we say get the test done, there are quite a few parameters. Again, we will look at the table. So if they are looking for a specific adverse effect, we can try to understand the cause and then look for those. If not, the usual water quality test will not be exhaustive. It will look at only a few aspects or such. So that's something to keep in mind. And obviously, as I mentioned, rarely do we look at radioactive substances, but if there are relevant side effects or such, maybe then we will have to look at the radioactive substances. And again, similarly, DDT and atrazine, if you suspect contamination, or you see issues with respect to fertility or lack of fertility, or increase in infertility levels or decrease in fertility levels, typically that's due to pesticides. And you have different neurological issues too due to pesticide consumption, even in low concentrations over time, then we will look at it. But if you say, hey man, get the water quality test done, at the usual price of, let's say, 3,000 rupees or so per sample, I can't, or one can't measure all the samples. That's something to keep in mind. But obviously, we will always measure or try to understand the bacteriological quality of drinking water. All this will typically have long term issues, as in I keep drinking this water over a period of time. Unless the concentration is so high due to, let's say, some accident or spill, let's say a radioactive substance or arsenic came into the picture at very high concentrations, then I might have acute or short term effects. But in general, I will always have what we say, or I am always concerned with these bacteriological effects, because we will almost always have immediate effects. And as we know, death due to diarrhea is one of the major causes of death among the infant and the more susceptible population, which is the children. So that's something we need to be remarkably concerned about in India. So let's look at the relevant code, BIS 10500 20112 code, I guess, right? Okay. So what do we have here? The second revision and such, all this is fine. Okay, drinking water source, okay, this is Bureau of Indian Standards, I guess. Okay, Bureau of Indian Standards, and we already looked at the link earlier. This is the revision. So from time to time, they revise and update based on the best available practices and technology, and needs to. Keep in mind that they also looked at the EU directives, US EPA, United States Environmental Protection Agency standards for drinking water, WHO guidelines and such. So it's more or less based on what we observe in India, and also what the other developed countries are doing or have done. They typically have more stringent standards, but we can't aim to achieve those standards right away, but it's a step towards those standards, let's say. Yes, and World Health Organization guidelines. So drinking water, as we mentioned, different kinds of parameters. The first one, the generic parameters. So pH 6.5 to 8.5, taste agreeable but no specific test. Turbidity, pretty much important, we have to measure this, 1, and certainly less than 5. Total dissolved solids 500 and 2000. One aspect I would like to mention here. So quite a few people now in India have these household water purification devices, right? Different companies, Aqua Life, Aqua Pure, WaterGuard, so on and so forth. Everybody typically tries to sell you this RO unit. The RO will have, or the effluent from RO will have very little dissolved solids, not 0, but maybe 10 or maybe 20 depending on how well it's working or such, right? And here the issue is that if I drink water that has only 10 or 20, what do we say, dissolved solids, that's not at all good for my health. And it even has effects on the cardiovascular system, right? And digestive system and such too. Again, I need all these ions, fluoride, calcium, magnesium and such in little quantities. My body needs that. Without it, again, I'll have, what do we say, issues, different issues over the time. So just saying that, okay, RO and get that done, as a solution for everything, that's a misnomer, if I may say so. So that's something to keep in mind. In general, the required or acceptable limit is 500, but 300 or 350 is what is fine, or 300 milligram per liter. Above that, you will start to feel some discomfort depending on where you have been living and how long you have been, what do we say, consuming that water. For example, typically people will say RO, but what is the, what do we say, the person coming to your home to install that RO unit, he will ask, what is the TDS that you want? So, okay, you can say 300, right? So that's one way, but he does not set the setting such that the water through the RO unit will come to 300. What he will do is, he will bypass some water so that some of the water will not go through the RO unit and mix some of the water coming through the RO unit, so that the final of these two streams will be around 300. Again, we will look at these aspects later. So, organoleptic and physical parameters, right? And then the general parameters concerning substances which are undesirable in excessive amount. This is something we looked at earlier. And one other aspect I would like to mention is that we also have the kind of test, as in if and when there is what do we say, doubt or confusion regarding the authenticity of the test or quality of test. So, you have the relevant method and the reference that's given out here. So, as you see here, aluminum, ammonia, barium, boron, but rarely would you see boron in typical waters. Chloramines, again rarely, but if you have a wastewater that's been chlorinating their what do we say, effluent, and you are drawing water from near that particular discharge point, obviously chloramines will be a factor. Chloride, yes, you will have it. So, that is why the acceptable limit is given as 250 milligrams per liter. As you see, it is pretty high, it is not pretty, what do we say, it is not toxic or undesirable even at relatively high concentrations. And then you can see the relevant standards. So, nitrates, this is something that we mentioned or discussed in the context of our wastewater, that high nitrates are not good for what do we say, drinking water, especially for or in the context of the infants. They will, or their ability to transport what do we say, oxygenated blood to different parts of the body will be remarkably affected. This is something we discussed earlier, and that is what I want to point out here, I guess, right. So, calcium, hardness and such, right, 200 and so on and so forth. Then we will move on to the toxic substances, which will have either carcinogenic or toxic non-carcinogenic effects, let us say, right. Some compounds can lead to cancer and also other non-carcinogenic effects, that is something to keep in mind. So, cadmium, cyanide and such. I am surprised arsenic is not here, they would have probably classified that here. Okay, that is another surprise. I am surprised arsenic is not mentioned, because that is a considerable issue in India at least. Maybe it should be in one of the parameters somewhere, but probably I am unable to find that out, right. Again, you can look that up, it should have arsenic somewhere or the other, right. Okay, so let me move on. So, here you have the toxic compounds or relatively more toxic compounds. That is why you see that the acceptable limit is much lesser here. And we talked about the disinfection byproducts. So, that is why we see the trihalomethanes, which are one class of disinfection byproducts, which are given here. In India, we have it at what, 0.1 milligram per liter for bromoform, which is 100 nanogram per liter or 100 ppb. Okay, here is total arsenic. As you see, it is pretty low, right, 10 ppb. And same case with chromium, total chromium. Why total chromium or total arsenic? Because arsenic and chromium exist in different oxidation states. Here we are talking about total chromium and total arsenic. Typical way to analyze these heavy metals is by using AAS or ICP-OES or ICP-MS and such. Cheaper method is to use AAS, atomic absorption spectrometry, right. So, we have the trihalomethanes, Radioactive substances, rarely will they come into the picture, so I am not going into that. So, pesticides typically based on the Indian context or Indian or information from what do we say, or experiences from India. So, that is why we look at these particular compounds, and here we come to the bacteriological quality. Note that we are talking about E. coli, thermotolerant, so on and so forth, coliform bacteria. In general, we do the total coliform bacteria, let us see, right. Again, why are we going to look at total coliform? Why is it? And in this context, I think we need to mention that we looked at total coliform and fecal coliform, two relevant what do we say tests, right. Total coliform encompasses this fecal coliform. Fecal coliform we look for, I think, in sewage or for when looking at sewage treatment plant and water from that. And here we look at total coliform, let us see, right. Total coliform, again, why is it? Because these are indicative of what do we say, gut bacteria or feces coming in contact with this water or contamination due to human feces, let us see, right. So, what is the limit? As you can see, for all the kinds of uses, all water intended for drinking, treated water entering the distribution system, treated water in the distribution system, everywhere you see that it should be 0, not detectable in any 100 ml sample. Why 100 ml? Because it is based on the MPN test, I believe, but again, in any 100 ml sample it should not be present, let us see. So, that is the relevant aspect. So, let us move on or come back to where we were. Okay. So, let us get this started. So, sample water quality report, I think from IIT Roorkee of water from Joshimath, I think lower Himalayas in Uttarakhand hilly area recently, I guess. Let us look at what we have. When we say water quality, typically at least this is what we do or people in our lab do. What are we looking at? Color. We are typically not, I guess, measuring that unless it is visible, then we do that. Hazen units, there is a particular way to be able to do that with a spectrophotometer. Odor, just by what do we say, using the nose, I guess, and pH is 8, relatively high. Again, that is characteristic of water that is what do we say, from the springs or so high up, right. It is not yet in contact with high levels of carbon dioxide maybe, or with other deposits that can lead to decrease in concentration of H plus or increase in concentration of H plus and thus decrease in pH. So, turbidity, even there we see that it is 1.8, acceptable limit is 1 and here 5, but please note that this is right from the stream, right, without any treatment. So, along with the flow of that stream, maybe some particles would have been kicked up and such, but you do see that there is still turbidity. In general, we look at turbidity as an indirect correlator or variable that has correlation with coliform or the pathogens. So, again we will come back to that later. Total solids 435, total dissolved 424. Keep in mind that if we look at these values and sum them up and play around, sometimes these values might be off. But again, the issue is that when we are looking at this test, typically they take 2-liter water and then try to filter and then put it in the oven and such. But again, the accuracy is going to be pretty much affected, especially when we look at these concentrations which are so low, let us say, right. So, that is one aspect to consider. Chlorides obviously pretty less, and all other aspects are within the reasonable limits, let us say, right. So, that is something to keep in mind. And more importantly, what about the total and the fecal coliform? Here we seem to be measuring both. Okay. In general, total coliform is what you measure. Again, both came up to be nil. So, this water is good for consumption without treatment too, right. So, that is one aspect to keep in mind. Maybe if there are sand particles or such, you can filter it with a cloth, but you can use this. But when it comes to Rishikesh, right, water quality of Ganga at Rishikesh, what do we see here? Okay, pH is relatively less, expected. Turbidity has increased. It can be due to the suspended matter or due to other aspects which we will look at later. Total solids, dissolved solids seem to be fine, all the other aspects to be more or less fine. But as you can see, the issue here is that total coliform, let us see, 26. Even though fecal coliform have not been detected, you do see that total coliform is there. So, it is indicative of what do we say, gut bacteria or contamination by human feces and such. If not human feces, more or less gut bacteria, if I may say so. So, this water is not fit for drinking. And one other aspect is this coliform, both may be fecal and total, will be exponentially high when we have different religious festivals, when people have or come to bathe and such. Let's say you have the melas and such, and that's when you are going to have it to be remarkably high. So you see the relevant aspect, even though the water might look good, right? You see that we have, or we need to be concerned, because there are considerable indicators that say that this water has pathogens, and that's one aspect to keep in mind. And in this context, you need to look at turbidity. Turbidity again looks at what do we say, how well the light is being scattered by the particles in that water. And typically we look at a particular size of the particle, I think 50 or 5 micrometers or microns, and that particle size is more or less very much near the particle size of most pathogens. And that's why turbidity in drinking water, or at least in treated water, or even in general water from the surface, you can use that as an indirect correlator for the pathogens. Again, we will come back to that later, but I wanted to mention that right now. So what are some of the other important parameters? So turbidity, what will it give me an idea about? It will give me an idea about the ability of the water to scatter the light, right? Why is this concerned? So I have these small particles in water, so it comes through. This particular test will have this detector here. So at that 90-degree angle, how much light is being, what do we say, scattered, that's what it will measure, right? So what are the causes? It can be inert like clay, silt, and some organic matter which is not inert. It can be plankton, it can certainly be pathogens, right? Some pathogens and other particulate matter. So on these organic, or especially on particulate matter or on clay, you can have pathogens thriving. So that's one other aspect to be aware of, right? So most effective scattering, what do we say, agent, the size is 5 microns, as I mentioned earlier, and this size closely matches with the size of your what is it, pathogens, I believe. Unit and measurements, we have a turbidity meter which is pretty easy to use, and the reference is the solution of silica dioxide, yes, and we use turbidity meter. The units are nephrometric turbidity units, or NTU, that's what you see. And turbidity in excess of 5 are easily detectable in a glass of water and are objectionable for other reasons such as aesthetic reasons, right? So that's something to keep in mind. Let's move on. Why do I need to look at turbidity? As I mentioned, it correlates pretty well with physical pathogen removal. Let's say turbidity 10 and pathogen of, let's say, 100 or so. Turbidity 2 or 1 and pathogen of almost 0 or 2 or 3. So that's one aspect. It correlates pretty well with physical pathogen removal. And more importantly, as I mentioned, you even have these handheld portable turbidity meters. It's pretty easy and cheap to measure. Negatives, obviously, it's only an indicator which correlates. It does not directly measure the pathogens, right? Something to keep in mind. So another aspect is, as we looked at, we can have UV, and if we have UV and turbidity, why UV? I want to disinfect the water, and my relevant pathogen is here, right? My pathogen is here. So the UV will be absorbed by the relevant particles leading to turbidity, or the pathogens will be shielded from UV. Same case if you have organic content, organic matter, and I add other oxidizing agents such as, let's say, chlorine or HOCl or ozone, right? These organic matter, which will again be taken up by or can be measured indirectly by turbidity, suspended organic matter anyway, will consume the oxidizing agent, thereby limiting the disinfection efficiency. Something to keep in mind. So pathogens, typically we look at total coliform. We don't look at fecal coliform. Fecal coliform is a subgroup within total coliform. So it also includes what do we say, microorganisms from roots of plants and such, if I am not wrong, and also from the guts of warm-blooded animals, so which includes human beings too, right? The organisms include viruses, bacteria, protozoa, and helminths. Yes, and in general we look at we looked at this figure earlier, and in general we are concerned with these bacteria, some of which can be pathogens, the ones highlighted, and protozoa. I think we looked at this Cryptosporidium, Sporidium and Giardia. And in the context of environmental engineering, especially in the context of anaerobic treatment, we look at methanogens, but typically RKA, they are not a concern with respect to drinking water quality, with respect to health concerns and such, but we are concerned about these bacteria and some of these eukarya, let's say, right. So, that is something to keep in mind. Obviously, viruses too, viruses which are not mentioned out here. Let us move on. So, what are the different sources by which you can have contamination of the water by pathogens? Typically, it is the fecal matter of an infected individual coming and mixing with the drinking water of another human being, right. So, that is what we have out here, and this test estimates the number of microorganisms of the coliform group, which are an indirect indicator or indicator of pathogens. Why do we look at this coliform or this indicator organism? Why did we or people choose coliform? Because it correlates very well with the pathogens that we release, or which are from our gut or from our feces. It correlates very well, and equally importantly, it thrives well outside our human body. It is not as if it thrives for a longer time only in the body. Then if I can't measure it outside in the environment or water, it is of no use. So, it can thrive well there, right, and it is easy to measure too, relatively easy, if not very easy. So, these are some of the aspects why we choose to measure or look at the coliform group, to understand or to try to see the presence of pathogens, and thus obviously looks at E. coli, for which we also find a mention, in the standard, and the Aerobacter aerogenes, let us see, right. And reagents used in this test, typically we look at, there are other tests, MPN, most probable number, that is what we typically look at. A specific type of broth that is conducive for these coliforms is prepared, and we have the tryptose, lactose and different phosphates and nutrients, and you prepare that. Again, you do not need to mug this up, and you are going to fill 17 tubes, but in general it is 5 times 315, right, plus 2, Y2, we have 16 tube where we add sewage, so that we know that whether the test is coming out to be right or not, so that it is a reference, right. Again, this is not standard or required, but that is what we do in our lab here, and 10 ml of distilled water, again to see that there is no false negative or false positive, pardon me, right. Cover and shake all tubes well for a second. So, in these sets, right, let us say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So, in the first one I add 10 ml of the wastewater, the second one I add 1 ml of the wastewater, in the last set I add 0.1 ml of wastewater, and also I add this broth that we prepare, let us say, right, and then we incubate it at a particular temperature that is conducive for growth for a sufficient period, which is 24 hours. So, when the color changes to yellow due to the acid, I think, being produced or accumulation of gas in the inverted vial, it means that there is a positive test. So, you can have sometimes, depending on the kind of sample, you can have a positive result here, but negative results in all the 0.1 samples here. Why? Because it is not that you have uniform distribution of the pathogen in the relevant or the coliform in the relevant sample. So, here there is, I would not say guessing work. So, statistics is involved, but again you have tables that will give you an idea about how to get this number. We will look at that soon. So, let us move on. Estimation technique, pretty simple. So, lactose broth, inverted vial to capture the fermentation products, the gas, and fermentation tube, I guess, right, and wastewater is put in 10 ml, 1 ml or 0.1, incubated. If it is negative, this is what it looks like. If it is not negative, you have gas, and also you will have some color change here depending on the kind of test. So, you can have positives here, right, positives and positives here, right, 10 ml, 0.1 and such. So, based on that we are going to look at it. So, in general, what does it mean? Let me also look at it. So, wastewater, so we are diluting it by 10 times each, right, each time, each step we are diluting it 10 times. So, the microbial count or the microbes also, it is supposed to decrease, right. So, that is what we have. Here there are too many to count, too many to count, let us say. Though we are not actually counting, some people can do this. You can count the, you can also come up with the bacterial count, but again that is not usually done, but can be done. Usually what do? This is what we do. We try to see to it that we put that dilution into this tubes for our MPN test, let us say, right. So, one set is out here. So, different ways you can count, but this is what we do in general, let us see. And where is the data? Okay, as we mentioned, if there is gas production and color change due to acid production, positive test. If there is no change, negative test. Again, we are going to incubate for some time at the right temperature, right. So, how do I get this? As in, how do I get the MPN? Here it seems like it is 3, 2 and 2 out of 5, right. So, how do I get it? So, here we are going to, I think, use the tables based on the Poisson distribution. So, here for a 95% confidence interval, here we are not saying with 100% what do we say assurance, but it is at 95% guarantee, let us say, all right, 95% confidence, I guess. So, we were looking at, I think, 3, 2, 2, right. So, where is 3, 2, 2? Okay, I can't find 3, 2, 2 here. So, anyway, let us assume that it is 3, 2, 1, okay, 3, 2, 1, yes. So, MPN is 17, let us say, right, per 100 ml, that is what we have. 95% lower limit is 7 and upper limit can be 40. So, but typical one is 7, but lower limit is 17, pardon me, lower limit is 7 and upper limit is 40, let us say. So, based on different what do we say combinations of positives, you will come up with this most probable number from this particular data, let us say, right. So, obviously, if it is all 5, 5, 5, you can't just say it is 1600. Thus, you will see, let us say in Yamuna, I think where MPN will say that it is in lakhs and lakhs, let us say, right. I think if not millions. So, that is because considerable untreated or partially treated sewage from areas surrounding Delhi, which are not covered by Delhi's sewerage network, will come into Yamuna, downstream of Yamuna. So, if you take a sample downstream of Yamuna, you will see that it is remarkably teeming with different kinds of pathogens and microorganisms. In that case, you will have to dilute that water a lot before you conduct this test, let us say, right. If it is all 5, 5, 5, what do you need to do? You obviously need to dilute it so that you come to a more measurable range, let us say, right. So, estimation technique, we already covered that. If not, another way is number of positive tubes by the ml of volume of the sample in the negative tube, volume of samples in all tubes, square root, let us say, right. So, this is another way to get the MPN number. So, as we mentioned, what is the limit I need to be concerned about? It has to be 0 in any 100 ml sample, right, 100 ml sample. So, disinfection byproducts, okay, let me try to get this done because we already looked at this earlier. So, why do I need to be concerned about it? We already discussed this in the context of wastewater. I specifically mentioned let us not chlorinate what do we say wastewater that is being discharged, but people do that here due to dubious reasons. When they can't degrade the wastewater well enough, but want to show the relevant regulatory agency that they can treat the water, what do? They chlorinate it. When they chlorinate it, obviously, you know, the chlorine, which is a oxidizing agent, can oxidize some of the organics, but you have very toxic or considerably toxic DBPs that are released into the aquatic stream, let us see. For wastewater, there are no standards for DBPs, but that is obviously what do we say remarkably foolish thing to do from the environmental point of view, but obviously people do not care a lot. But with drinking water, it is toxic to me. So, as we saw in that Bureau of Indian Standards, we had the relevant limits specified for one class of it. So, we already looked at this. How are these formed? Disinfection byproducts. So, byproducts of disinfection. When I am adding a disinfectant, typically Cl2, HOCl or such, when they react with organic materials, you know, we have this. We already covered this in detail when we looked at the relevant DBP formation in the context of wastewater or disinfection of wastewater. So, types of DBPs. In India, at least trihalomethanes are what do we say regulated. So, I think this is not from Indian context. Let me just check right away, right. Where do we have that? Okay. So, obviously, we have much higher standards out here. So, this is I think from US EPA. My TA might have forgotten to remove it. So, obviously, as you see, their standards are pretty low, 80 ppb, but for us, for each one itself, we have it 100 ppb or so, total is 500 acceptable. But again, that's because our plants and our standards are still what do we say, not up to scratch. But you see that we want to improve the quality of life, then obviously we need to look at these aspects too, right? This is not from the Indian one, I think this is from US EPA. Indian one, we can look at the relevant standard. So residual chlorine, typically we want that. Why? Because otherwise if you have pathogen re-entry into the distribution system, or entry into the distribution system, or microbial growth, you can have issues at the consumer end. So that's why you want to have some residual chlorine even at the furthest point. But if it's too high, again it's going to be objectionable. Obviously chlorine is a strong oxidizing agent. So there are other, what do we say, other disinfection byproducts which are not regulated in India due to various reasons. But for example, like haloacetic acid and such, for which in the developed countries we have the relevant standards, but in India we do not have that. So that's something to keep in mind, let's say. Again, bromate formed when Br minus reacts with ozone, that's also regulated there, right? So lead and copper of greater concern in the US, because earlier they used to have lead or copper pipelines. So corrosion product of the distribution system, typically water can have an oxidizing capacity, and it can lead to corrosion of your relevant what is this pipeline, or again relevant aspects. So what are the side effects? Interference with red blood cell formation, certainly kidney damage, and then cognitive performance, let's say, is also going to be affected. Cognitive performance, let's say. Allowable limits, I guess hopefully these are from Indian context. Let's have a quick look at that. We are looking at lead 0.01. So looks like they did get it right this time. For India, these are the standards. Again, as you see, they are pretty less. Again, these standards are developed based on the risks associated with a particular compound to the particular human. We won't go into that. But again, we now understand the kind of water that we want to be consumed. But one aspect to note is that when we do a drinking water quality test, we won't obviously look at all these 100 or so parameters. We will look at the usual few, and even then if you suspect something, then you need to dig deeper, but obviously then the costs increase. So with that, I'm out of time for this session. So thanking you for your patience, I will end today's session.